So it's a pleasure to have Ahmed Almheiri give us a talk about measurements with probabilities in the final state proposal. We might do this again when Raphael comes in.
Okay, thanks a lot for the chance to speak. So this talk is going to be about the information paradox and also the firewall paradox. So before we begin, I think everyone should take a very deep breath, just relax. I was going to say that if you're Raphael, take 2 deep breaths, please. Okay, so the outline for the talk is this. So I'll start with the review of the final state proposal. Then I'll review the so-called Busseau-Stanford paradox, which is a seems like a very big deficiency of the final state proposal. Then I'll discuss how replica wormholes are, how we can gain insight from replica wormholes to modify our understanding of the final state. And then I'll end with that main lesson and how the final state can actually make sense and evade this Busseau-Stanford paradox. So let's begin with the final state proposal. So the issue is that we need to get information from inside the black hole out, and this can be done if you use post-selection, which means that you suppose you assume that there's some final state projection that happens on the black hole singularity. The rationale, there's a quote by, this quote is it's not a direct quote from Gary Horowitz, but in spirit, it is. That initial states of we like to associate initial states to Big Bang singularity, so why not final states for future singularities? Okay, the condition that you need in order to get all the information inside the black hole to get out is that you need to project onto a maximally entangled state between the infalling matter and the inside Hawking modes. Okay, and it has to be maximal in order for there to be a sort of direct line from the inside out. And you can see that here. Here's a circuit diagram. You have the infalling matter coming in. You have some projection onto a maximally entangled state with some unitary on one side. And this entangled state here, phi for me is always going to refer to the maximum entangled state. It's between the inside Hawking modes and the outside Hawking modes. And the resulting state of the outside Hawking modes is going to be S times I. So S you should think of as the S matrix. You see what else I want to say here. Okay. Oh, there he is. Well, this is the title. Okay. So far I just reviewed the final state proposal. Let me see what else. Okay, just some comments on the proposal as written. This is what you would write down if you had. This is the final state proposal for the sort of complete evaporation process, right? In this circuit diagram, the entire black hole got projected on in a sense, and all you're left with is just the radiation outside. Okay? I can discuss later a model for what sort of a final state for a partially evaporated black hole, but I'll leave that to the very end if need be. But everything I'm going to say today is not going to depend on that. There are some issues with the final state proposal, namely that, as Lloyd and Prescott pointed out, it's fragile to interactions in the interior. So if you allow for interactions between the state I and the interior modes, you can find interactions that, for example, when it gets projected on, you would get 0. So nothing gets mapped out. Oh, no, you're right. Okay, sorry about that, thanks. One way to avoid this problem is to replace this final state projection, not with this simple projection that I have here, but instead with a random final state that acts on all of the entire index for the matter and and also the infalling particles. Okay. Actually, first, are there any questions so far about the final state? Okay. Just to make things simple, I'm going to ignore the infalling matter and just focus on radiation. So I'm going to take my black hole to look something like this. So basically, I just have a bunch of infalling modes, maximally entangled with outgoing modes. And the state on some slice here is given by the state psi, which is, I've split the Hawking radiation into what you can call a late mode, B, entangled with its partner B tilde, and early radiation R entangled with R tilde. And then there's going to be some final state projection. In order for R to purify B, you need to impose the following condition on the final state on the singularity, which is that if you were to trace R tilde, you should get a maximally mixed state. Okay? There's some funny normalizations, which I'm going to ignore. If the final state satisfies this, then you find that B is maximally entangled with R. Now let's discuss the AMPS experiment. So in the final state, the claim is that, so the AMPS experiment involves two experiments. One where you check that the mode B is entangled with the early radiation, the late mode is entangled with the early radiation, and that the late mode is entangled with its partner. So I'm going to call those a unitarity measurement and the no drama measurement for historical reasons. In terms of this picture and the circuit diagram, it's probably better. It's easier first to look at the no drama measurement. That's just a measurement, just checking that B and B tilde are in the maximally entangled state. The unitarity measurement just checks that B and R are in the state that you claimed to have prepared them in. Okay. So this is, as we said before, this prepares B and R in a state where B is maximally entangled with R. And the claim that the AMPS experiment succeeds is that the probability for either of these measurements computed in this way is equal to 1. Right? So what am I doing here? I'm starting with the state psi. I'm then inserting a projection, so I'm doing a measurement. Then I'm projecting with the final state. So this is my new state having done the measurement. And now I'm just taking its norm. Okay? That gives me the probability for that measurement to have happened. Let's check the claim. So first, let's compute the probability of having no drama. So let's look at this picture. So you start with R tilde entangled with R and B tilde entangled with B. You move up the diagram. Here, I'm inserting the measurement, B tilde B. Then I'm propagating forwards again. I'm projecting inside the black hole. So I have my state. And now I'm just taking its norm. And you can check that this is equal to 1. I'm using this relation here. So the horizon is smooth with probability 1.
Can I ask a question? So
yes.
You said you're going to ignore normalization, but now you're computing probabilities. So
in one of my diagrams, I was not very careful with the normalizations, but when you compute the probability, normalizations are important, and they are all included here.
Okay, so you're just saying you're not including them because you have to renormalize the wave function when you do the final state projection. Right?
Yes, that is taken into account. I don't know where, but it is.
Great.
Thank you. Okay. Then there's the unitarity measurement, which is, so again, you have the maximum entangled state. Then you have this projection. And you take the overlap, and again, you get 1. I mean, this is kind of trivial because you're just projecting F on F. Okay. So the evolution, quote unquote, is unitary, also with probability 1. But then the thing that Raphael and Douglas showed was that if you were to compute the probability of the actual AMPS experiment, which involves two measurements, the unitarity measurement first and then the no drama experiment, then you get a different answer. So the order follows just from causality. So here again, you have the entangled state, you do the unitarity measurement, then you do the infalling measure, the no drama measurement, and then once you're done, you project. And you compute the overlap and you get 1/2 to the 4. Okay. So the probability is, yes.
Is there a reason why you're not writing the unitarity measurement just as a projection onto the expected entangled state? Why are you involving? I mean, F is one way of getting that, but
yeah, you're asking, for example, so notice that R is much bigger than B. Okay, so you're imagining that I first decode from capital R the bit that's entangled with B, project on that, and then re-encode R back in, for example.
Yeah, whatever the purification of B is,
yes.
You extract that, you do the measurement, or you check that they're in the correct L state or whatever they are in.
You get the same answer. Everything I'm going to say today is.
Of course, you get the same answer. I'm just asking why you're writing it that way.
It'll become clear in a sec. Okay. So here are the probabilities again. Was there a question? So 1 for each, but 1/2 to the 4 for the combination. So the issue that Raphael and Douglas pointed out is that the statistics, Mr. Esther, of the unitarity measurement seems to depend on whether the future no drama measurement takes place. Yes.
Sorry, I've probably asked you this before. I always get confused by this, but why do you necessarily have to interpret this as saying the future measurement got affected by the unitarity measurement as opposed to saying me?
No. It's the first measurement, the unitarity measurement gets affected by whether you're going to do a future measurement or not.
But given that the thing you're computing is a number which involves both pi b tilde b and pi br, why can't I interpret that as saying I acted on the radiation and it affected the outcome I would have had when I jumped into the horizon and measured whether the vacuum is smooth or not?
No. So this says that if I do a measurement just on the outside guys, I'll get a definite answer with probability 1.
Yeah.
This says that I might find a different answer for the outside measurement if I suppose that in the future I'm going to do the B tilde B measurement.
Yeah, no.
So that's go on.
No, I understand that that's a causal, but I'm just saying, why does the third line imply that necessarily and not just saying that it affected the outcome of the infalling observer's measurement, as opposed to saying it affected the outcome of the unitarity measurement? I just don't see where where the asymmetry is that tells you that you have pi b tilde b probability is 1, you have pi br probability is 1.
Well, there's a non-zero probability in the second line. You have a non-zero probability of seeing something wrong for br. In the first line, that probability is 0.
No, I guess I'm just asking how you know that it's wrong for seeing something for pi br as opposed to just pi b tilde b.
I think at the level of what's written here, it's hard to see. But if you take into account all the other possible measurements of B tilde, anything you get will correspond to a smaller than 1 measurement for BR.
Oh, I see. Okay.
The fact that it's 1/2 to the 4 says it's completely random for all measurements.
I see. Okay.
So we're all used to the fact that the probability of X and the probability of Y, that the product of them is not the probability of X, Y. But here we have probabilities 1. And if something is certain to happen and something else is certain to happen, then they're both certain to happen. So can you explain how I can get 1s for the individual events, but not 1 for their joint
hence the entire paper of Busso Stanford. Like that's why the final state seems bad.
Good. But then, first of all, I don't understand how we arrived at this, because it seems like all you were doing is matching, like drawing diagrams with lines, but that just follows ordinary quantum mechanical.
No, just because it's not ordinary. It is not ordinary quantum mechanics because I have these things, have projections that happen. There's post-selection involved.
Okay.
So far. Okay.
I think.
That's right.
If Daniel were here, he would say, these are consistent probabilities. It's just that you have to swallow a causality. And that's, so there are probabilities, but they're a causal.
Okay, I don't want to swallow a causality. Okay. Okay. So one comment I wanted to make is that there's something suspicious here. In particular, these measurements don't account for the fact that B tilde is part of R. Okay? And this is going to be what I'm going to try to make more manifest in the remainder of the talk. To do that, let's consider replica wormholes, that I'm going to use the PSSY model. This is a picture here in Florence. Weren't sure what it actually stood for, but yeah, probably like some gang here or something. Okay. So what I'm going to do is I'm going to want to think about the black hole interior as a closed universe. Okay. Is there a question? No. So here in this picture here, for those unfamiliar with the West Coast model, here the black line is the ADS boundary, and it's just before you get to t equals 0, it gets capped off by 2 end of the world branes. And I have 2 boundary degrees of freedom here or particles that fall into the bulk. And think of them as like this R tilde B tilde, in the sense that R tilde is much bigger than B tilde. So this is the first claim. The second claim is that the replica wormhole story in a precise sense can be thought of as having a random final state where you draw your circuit diagram with putting F's everywhere, and then at the end you integrate over F, you randomize over the final state, and all the contractions that you get from doing these hard integrals are essentially what you get from having wormholes connecting different boundaries. Okay. Next, let me introduce something which I'm calling the Z2 rule, or the Z2 rule, for assigning the bulk dual. This is something that everybody does, but I just wanted to be very explicit. So it's sort of an answer to the question of, given a state, how do you assign to it a bulk spacetime that is appropriate for doing sort of semi-classical measurements? Okay. So the first step is I hand you a state. So say a state like this. What I do is I compute the norm. This is what the norm looks like. I look at the dominant saddle to that norm. So I fill in the spacetime here, and then I slice it in half. Okay, and so then I have this. So then the claim is that this spacetime here, obtained in this way, is what's appropriate for bulk semi-classical measurements. Let's do another example. So let's think of how Petz reconstruction works. So let's say I give you a state, you can call it a state in the code subspace A, where the blue particle is in some state A. The Petz operator that can change A to B looks something like this in this simple model. It's just bracket of this guy. The new state is just obtained by acting O on A. Then to get what the spacetime looks like for the state psi, I compute the norm, which looks like this. And I fill it in. I look at the Z2 slice, and that's what this gives me. Oh, sorry. It's this guy, but unfilled. Yes. They are boundaries of this of the CFT or the quantum system, and they prepare for you a closed universe on at this t equals 0 slice. Rectangular line. Sorry, is it important that I put these red dots here or not? Is that the question?
The whole horseshoe thing, is that important? It's not,
It is important.
I mean, not every state looks like, it seems like you're on the one hand discussing something extremely general. And on the other hand, it's tied to this particular setup with end of the world brains or BCFT. And I'm a little confused how general we're being while at the same time drawing these pictures.
I want to make a statement like this. I want to derive or assign let me see. Well, I want to assign my state a semi-classical dual. And well,
And what you want to say that the Z2 rule is very general, but he's going to examine your proposal or your paper with Douglas in the context of the specific model. So he's just using these diagrams in preparation for that.
you can think of it like that, yes. Yes, yes. Question?
Yeah, I think I have a question here. So this Petz operator also involves this horseshoe, but that's some auxiliary system. Is that right?
Correct. It's what Douglas likes to call the simulated black hole that you bring in, which helps you, well, interchange the state of your system.
Okay, thanks.
Okay, then let's do the AMPS experiment. Okay. Yeah, just thinking of Raphael's question, I kind of agree that I didn't really need to use this horseshoe. I could have done this just with the original circuit diagram. But let me get to that later. Okay, so for the AMPS experiment, I'm going to start with the projected state. So you should think of this horseshoe as the thing that projects on this entangled state. Then I'm going to do this is the norm of having done the unitarity measurement, okay? So this is the projected state, this is the unitarity measurement, and another one, and then the bra. And that looks like this, and the colors are it's color-coded. The upshot is that when you look at the dominant saddle of the norm, it's just this guy. Well, it's this thing. Then you look at this, you consider the Z2 rule, and that assigns this measured state the following bulk dual. And if this is what the bulk dual is for semi-classical measurements, then you can just perform the node-Drummond measurement on this state. And what that involves is just inserting the measurement of B tilde B on on B tilde B here. But the thing to notice is that the measurement happened in the B tilde B that were part of the yellow shaded region, which is part of the projector. Okay? So the point is that there's a new, so now I'm not using the horseshoes, I'm just using these the original circuit notation. The new rule is that the measurement checking unitarity introduces a new final state and a new interior. And yeah, go on, Raphael.
Yeah, so maybe now's the right time to ask this question again. You could have presumably represented the same thing by just inserting a complicated unitary, checking that B and its purification are in the right state, and then undoing the unitary, and you keep going. And if I had made a somewhat simpler measurement on the radiation and B, that's probably what you would have actually done. Like if I hadn't made a measurement that checks that they're in the, that complicated measurement that checks that they're in the correct state, but just checked some 5-point function. And as you know, what I'm struggling with here is to understand when you represent a measurement in this way versus some other way. In particular, I'm worried that you can write the identity involving things like this. And you could, however, you're not going to get the exact identity because this actually degrades the state a little bit because you're.
But that's the key, a little bit.
Yeah, but if I was free to insert these things, I could insert many of them and degrade the state. I'm just.
But it will always be by
I'm
a
just
small
trying to make
amount.
the point that we need some rule for when to represent evolution or a measurement by introducing a new interior, a simulated interior, and when not to do that and just do the usual thing. You seem, to me, this is like pulling it out of the hat a little bit. Like, well, why not just write a unitary, check that B and its purification are in the right state and keep going? Why did we invent this new interior?
No, so you could have done that, but that unitary will depend on the details of the final state. And if we were to,
It'll depend on the estimate.
yes,
That's it. It's one unitary. I put it there and keep it. But then you wouldn't get to say the things that it say about the unitary.
no, I think you would have. Maybe this is an issue of, so in calculations that we can actually do using semi-classical gravity, it would always involve things like, well, the unitary that decodes the message is going to be, let's say, drawn from an ensemble, but that same unitary is also going to be involved in the final state of the black hole.
Douglas and I, following Ham's were doing semi-classical gravity. We were assuming we have knowledge of the full S matrix and we can directly check. We're capable of doing this complicated experiment. We're just thinking of it just another unitary, whatever, that extracts the purification, then you check.
So let me see. So I agree that I can work, for example, I can work in these pictures, which doesn't involve any averaging or anything. Okay? And I can just follow rules for how to contract Fs together, which just descend from saying you have a unitary S matrix and so on. And well, a rule I can give you is to say that you should. Let me actually use this. So something you can do here is something you can do here is you can sort of simplify the circuit. Okay, so if you simplify the circuit, then this guy cancels with this guy, and then all you're left with is just one of them.
Yeah, but my question comes earlier. I mean, I thought that's the goal, right? You're introducing this pair of new Fs so that in the end you're left with a new interior after you got rid of the old interior, and that's very beneficial and sort of the key point. And my question is, for which types of measurements do you introduce new Fs versus just saying, hey, I made a simple measurement. I'm going to, just put projectors onto whatever, states that I'm distinguishing with my projective measurement and represent it that way. And I think you're going to say it has something to do with the complexity of the measurement. I'm just trying to get you to say that.
No, but it's not. It's not about the complexity in general. It's about whether the measurement depends on the S matrix or not. Right? There are complex measurements which are from the, let's say, ensemble sense, is drawn from a different, like a unitary transformation that is drawn from a different ensemble than.
All measurements depend on the S matrix, just very little.
What do you mean by that?
I mean, even the 5-point function depends on the S matrix just by an exponentially small amount.
But it's not inputted into the measurement. Like it's for different theories, it's the same operator. It's not a different operator in different theories.
We have only one theory, I'm assuming here. I'm
Okay.
assuming that when I make a black hole and it evaporates in the real world, it's described by a single S matrix. There's some calculational tricks we can sometimes do where averaging is helpful to us, but there's only one S matrix. And I'm just gonna, I know it already. That's sort of the usual presumption when we discuss the information paradox, right? And I can, so I don't get to think of a particular operation that I do or a particular measurement that I do as depending on it. It's not a well-defined notion. It's just a measurement. It can't depend on the S matrix because I don't get to vary it.
I see the perspective, but I feel that that's okay. Maybe there's a deeper truth to this that is sort of outside the scope of what we can actually calculate now. But in terms of what we can actually do in terms of these Replica wormholes and things like that, we have this additional handle where we can actually vary over S matrices and so on.
Yeah.
Which tells us, gives us a handle on which measurements operations depend on that.
Would it be fair to say that this sort of formalizes or puts into circuit diagrams the same apparent tension that we have in the Pennington/AEMM calculation, where we see a smooth horizon, and yet we get the page curve? I mean, there's, on the one hand, if I just looked at the space-time picture, it looks like Hawking was right, and I have to trace over the interior, I'm going to lose information. But then when I actually do the calculation, I find I don't. I mean, I think that's sort of what's, but to get that, you know, I have to embrace some kind of, well, it seems like we have to embrace some kind of ensemble or some kind of averaging. And that's maybe the resolution here, that this is similar to that.
I would say it's related. I'm not sure if it's exactly the same, but in what's happening here, I would say that that there might still be hope for the final state with a summary interpretation like this. If we successfully sort of list all the rules, maybe we just haven't found all the rules for the final state. But clearly, if something like this does make sense, then it seems like there is a way to at least evade one paradox, meaning the Stanford paradox.
I think a really interesting question is whether quantum mechanics is fundamentally correct. I mean, not final state quantum mechanics, but actual quantum mechanics. And I think that's when we embrace an ensemble as sort of a fundamental ingredient in what we're calculating, that's probably not the case. And
oh, sure.
yeah.
No, I meant
trading the final state for an ensemble, I think there's a conservation of misery somewhere there.
No. So sorry, no. I'm not replacing. I'm not substituting ensemble averaging with a single final state.
No, what I mean is you're rescuing the final state that from our point of view was associated with a single S matrix. I think you're making it look more consistent by associating it in some sense with some averaging, which allows you to then distinguish between the cases where you should insert, where you should represent a measurement like this versus in some other way.
Okay.
I think it makes sense that you're able to do that. I'm not saying that's not a useful thing to do, but now I understand it better. Yeah.
Okay. So I actually didn't have much more to say. This was just the two calculations side by side. This is one. So here's where the measurement is embedded inside the operator. It's not. It's not my fault, Raphael. I mean, it's, you have to pick your collaborators intelligently. Okay. Okay, that's really everything I wanted to say. So the hope was that from replica wormholes, maybe at least in this ensemble averaging context, it provides a new rule, and which sort of removes the causality of Stanford And so then there's a hope that there might still be some consistent set of rules for the final state yet to be completely found. Thank you.
Questions? Yeah.
Thank you for the very nice talk. In the calculation that you showed on that one slide, this one, and I guess also the one before, yeah. So when you're measuring unitarity, the way you're doing it, I guess, is more like distilling the amps qubit, measuring that it's maximally entangled, then like re-encoding it back before, and then so that when you jumped back in or jumped into the black hole, you would see a smooth horizon. I see. And,
I'm not sure if this is exactly that, but it's one can also consider that measurement.
you would agree though that after doing this measurement, you would see a smooth horizon. Isn't that what one thing you say in the previous?
Yeah. So that's the claim is that that's what this picture is supposed to represent. Doing the outside measurement first, and then jumping in to check the no drama measurement.
And then you would get no drama.
Yeah, probably one.
And so I imagine that you can also write some calculation in which you say, do the unitarity experiments, but then like decide to, I guess you can fuse this with your Petz calculation to change what you would see at the horizon.
Oh, yeah.
And then, so, yeah. So all that's also encapsulated.
Exactly. So I guess what Chris is asking is, suppose you, let's say you follow the, let's compare Bussow-Stanford with the new calculation, and instead of doing these measurements, you do something else. As you're falling in, you collect the radiation and you change the state of the interior. And then you jump in and you check that what you actually did was implemented. In the Bussow-Stanford way of drawing things, that would not actually happen. You actually have a frozen vacuum. The interior is going to be this part, which doesn't get affected. Maybe I should go up actually. Right here. So in the Bussow-Stanford discussion, when you jump in, you would see this part. So the state was initially A, and you jump in, you'll see it A again. But in the new way of thinking about it, the interior is the part is the thing that came from the operator. This is the new interior that if you jump in, you would see. So
yeah.
Can I have a question? Hi.
Oh, hey, Shalian.
Hi, Ahmed. Yeah. So I wonder how important is the fact that the projectors you draw are rank 1. I mean, in practice, I can do a projective measurement and know something, and there could be other things I don't need to touch. So it could, in general, is a higher rank projector.
So the rank 1 projector is appropriate only for the completely evaporated model. So if you can consider a black hole that's just partially evaporated, then instead of rank 1 projector, you actually have to put a final density matrix, not a final pure state. And informed by the replica wormhole story, the final density matrix has to be placed anywhere on the island.
Sorry, I don't mean the projector at the final state. I mean the measurements you introduced. Well, in your diagrams, they are projectors with rank 1.
Yes, okay. But so what kind of measurement were you thinking?
Like I take B and some part of R, which are partners of B, and then I could measure them. But there's other parts of radiation that are not entangled with B. So my projector does not act on them. So in general, the projector is not rank 1. I don't need to take a pure state and project my entire radiation to some pure state.
Yes, no, that's related to another question that was asked. You can, everything goes through. This is just for simplicity. You can consider the case where you decode RB, do the measurement on just RB, and leave the remainder of the radiation alone. So this would not be a rank 1 projector, as I think this is what you just explained.
Yeah.
And everything goes through. Nothing I said depended on whether I did this or that.
Okay, thanks.
Yeah.
In the context of Raphael's question, I was curious why you weren't happy with just saying that even if you artificially represent certain operators in terms of the final state basis, when you actually go and compute correlation functions, the like other saddles that are necessary to like replace one interior with another interior are just going to be suppressed. So there's always going to be some small overlap with these other interiors, but they're just not going to be important unless the operator you're actually like acting on the state with, you know, has enough, like say in this particular model, dependence on the like the end of the world brain to actually like enhance that contribution or something. Or is that just too naive a picture?
I think actually all three of us agree with that statement. I think so, because in the context of the question assumes you have ensemble averaging, because you have some space times you have to fill in and so on and so forth. I think Raphael was asking more about like what's in this diagram. There's no averaging. You just have a given F. Although maybe one can, well, unfortunately, I wouldn't know how to do the calculation. It would be very difficult for me to compute some correlation functions given some random F that's not, at the end of the day, averaged over. So whenever I try to answer Raphael, I always get pushed into averaging.
I see. Here you're defining the final state. Okay, but your prescription for the final state is via averaging, right? I mean, it's essentially just the Wormhole prescription.
No, so well, yes and no. Here, well, actually, yeah, no, you're right. And on this slide, the final state does involve averaging, but you might have hoped that on this slide, everything is defined without averaging over F, which I think is going to be true. For example, there's a condition. The only condition that F needs to satisfy in order for this to be correct is was this condition that this is B, but this is a maximally mixed state. Which I'm sure you don't need to assume ensemble averaging for this to be true. Yes, Rafael?
Yeah, I think I agree. Once you've drawn the diagrams, it doesn't matter whether you're averaging. I think the need for the averaging is sort of hidden implicitly in the need for a rule by which you decide whether you involve F in representing your measurement or not. And Ahmed has a very clear-cut rule, which, however, requires you to have this notion of averaging. If the measurement is the same independently of, you know, which instance we're in, then you don't put the F there. And if it depends on the final state, then you put the F there, and that makes sense. But that's where I think if you take away the averaging, then you lose the rule.
But shouldn't we use the results from averaging as a prediction for what a given F would, a given circuit with a given F would give you?
I don't know what that means. I mean, when you're doing a calculation, you need to have a rule for when to represent a measurement involving in a way that involves F and when not to do that. What you do after that is up to you, but that's a choice of how you do the calculation for which there has to be a rule. And I don't know how to, I mean, maybe there's a rule that you can come up with that doesn't invoke averaging, but right now it does, and it makes sense to me that it does.
Well, I can give you a rule here that, this might be an ad hoc rule. So let me just say it, which is the simplification thing that I said before. So, so let's say we're trying to simplify this diagram, and we're trying to pin down which of these F's is the interior.
But I'm asking why you drew it that way in the first place. Once you have that diagram, you can do whatever you like with it. But why did you introduce these F's in representing a measurement rather than just putting a unitary there?
Okay, I see.
Further questions for Ahmed? Okay, if not, let's thank Ahmed again.